Is it on now? Can anyone check? You might be having a notification. Yeah. I'm extremely sorry, guys. Like I assume that the recording is there.
Someone has stopped it. It had started once.
Okay. Okay. I expect that this is not repeated then. Uh, Fine, I'll start again. Okay, so this is the head available to you throughout the section, 15.5 meters, and you have to ensure that at least 12 meters is available for the distribution system. So this is okay. Likewise, now at point B, just a minute. Yeah, over here for point C, you know that 215.5 is there. Just a minute. I think I have done something wrong. Give me a minute, please. Okay, let's see over here. Then was here, and then 200, then 195. Okay, okay. So now, mm, okay. So let's start comparing now. So 225 meter head was available over here. The head loss is 9.5 meters, and we get 215.5 meters. Okay. So this head minus the head loss is this much, and this is greater than this value. So that is fine with us. Also, for this portion, guys, just give me a minute. I think I might have confused somewhere, or else someone can help me.
This head loss which you have calculated, that will give the value at B, right? At A it is already given to be 225.
Right, right, right. Thanks, whoever it was. Yeah, and this, if we subtract it, that amounts to be 15.50 meters, uh, and this is greater than 12 meters accordingly. Right, and again after that, this is the head available over here, 215.50, and 215.50 minus the head loss over here, that is 8, amounts to 207.50, like this value. And if you subtract 205.50 minus this, you get 12.5, which is again greater than 12 meters. Okay, who was the one who helped me? May I know the name?
Ishan.
Okay, Ishan, so am I correct now for the next step also?
Yeah, I think so.
Okay. So this is how you ensure that the design considerations are met and the head is met. That means accordingly the terminal pressure concentrations are also met. Okay. And since nothing is given about the maximum allowable pressure for the pipe, so mute. Thanks. So this was the first type of numerical which you might be getting in the paper, in which you have a simple distribution network and you have to calculate the diameter of pipe, like the pipe sizes, and ensuring that the design considerations are also met. And in this particular case, the design consideration was given in the form of the terminal head, which needs to be available throughout the distribution system. Moving on, the next thing is the Hardy-Cross method. I'll try to quickly go through it. How many of you have a class at 9? Don't raise the hand, just open your mic.
Most of us will have. Most of us have class.
Right. So I'll try to cover. If we are not able to do it, we'll continue this thing again. But we'll start. Now Hardy-Cross method is for sections like this. So let's say if you are given over here that there is a closed loop, then these looping things are called the complex networks. And if we want to determine what flow is there in each pipe, each line represents a pipe, what flow is there through each pipe, that is calculated, that flow is calculated using the Hardy-Cross method. And basically the Hardy-Cross method was analogous to the statistically indeterminate structures which we do in the structural analysis part, because he was basically a structural engineer and he used the same concept which is used in structural indeterminacy, the same concept in the water section, the pipe distribution network. So the main fundamental behind the Hardy-Cross method is that you need to ensure that the law of continuity is followed. That means that the pressure drop around each loop is zero. The sum of pressure drops around each loop is zero. This particular thing, and also the flow entering a junction is equal to the flow leaving a junction. This is the main thing with which you start the numerical. Okay. So the stepwise thing is that you assume certain flows in a pipe. Those flows are assumed keeping in consideration this particular law of continuity. Once you know the flows in a pipe, you calculate the head loss. The loss of head is calculated in a different manner over here. Then you calculate the correction factor for each flow, of pipe. You apply those correction factors to each pipe flow, right? And you see whether those correction factors are high or low. If the correction factor is very high, that means let's say you decided that a particular flow 25 meter cube per second is flowing through a particular pipe. You got a correction factor of, let's say, 10 meter cube per second. This correction factor is very large. So what we do is, that means we need to follow another iteration. And when we do another iteration, you see the correction factors in the next iteration. If it is again, let's say maybe 6, then you perform another iteration, and once the correction flow is less than 5 meter cube per second, then you stop, and this thing is repeated for all the different loops which exist in the pipe distribution network. So we will start with it. Now this particular thing is only to determine the flows within the each pipe system. So let's say if I name them A, B, C and D, then in that case you need to determine the flow which we will be going through this pipe, the correction in that flow, and whether that correction is greater than 5 meter cube per second or less. Okay, or 5 meter cube per second, 5 liters per second, whatever the units are given to you. But in most of the cases you are not given the units, they directly give you the values. So let's say 50 meters cube per second. I'm assuming the units is meters cube per second. So 50 units of water are coming from here. This K is basically, you remember that formula, 1 upon 0.094 Q by CH raised to power 1.84, 1 by D raised to power 4.87. This was the formula of head loss. Okay, using the Manning, this was the Manning's formula. Now this head loss can be somewhere written as K into Q raised to power N, if we know the diameter, if we know the CH value. CH value is usually 100 for cast iron pipes, which are generally laid down in all our cities, and D is also, let's say, given to us. This is assumed in the Hardy-Gross method that we know the value of D, and once we know D, once we know CH, we can write this per whole head loss formula in this particular way, right? And this is that K constant given over here. So you are assuming, when this is given to you, you are assuming that diameter of pipe is known to you and material of pipe is also known to you. Like you would know the CH, you know the D value, and accordingly that's why you know the K value, right? And this N, Q raised to power N, this N value is also usually given to you. If not given, then in most of the cases you assume this value to be 2, right? And that is what we will be doing in this particular question again. So coming back to the distribution of flow, we need to ensure that through each junction, the amount of flow entering is equal to the amount of flow which is leaving that particular junction. So 50 is coming over here, K is equal to 2, K is equal to 2. That means they might be having similar diameter and similar material, so the flow might be distributed equally. That is 25 units here and 25 units are going over here. Now at this particular point, the law of continuity is maintained because 25 leaving is 50 and 50 is entering. Coming at this particular junction, 25 is coming from here, 50 is coming from here. Something has to go over here and something has to go over here. And make sure that no pipe is left empty, because if the pipe is existing, that means some flow needs to be passing through that particular pipe. Okay. So we need to now see how much flow to be sent over here and how much flow to be sent over here. And there is a general thumb rule that if you are using the units 25 and 25 over here, try to have the same kind of units over here also. Like here 50 and 25, total 75 incoming. The outgoing should be in the form of 20 multiples of 25 only, because that helps with the calculation part. Okay, so this has a greater head loss since the K value is high, so we will keep a greater flow. That means we will keep 50 over here and we will keep 25 over here, right? You can keep vice versa also. You can keep 50 over here, you can keep 25 over here, but obviously if some pipe has some greater head loss, we prefer to have a greater flow through that pipe, so that the minimum head or the minimum head requirements are ensured. So 25 is here, 50 is here. Now at this particular point, 25 and 25, total 50 is coming and 25 is leaving. That means here whatever will go is 25. And at this particular point, 50 is coming from here, 25 is coming from here, and 75 is leaving. So that means our system is complete. So what we have done is, so this is 50, this is 25, this is 50, this is 75, this is 25, this is 25, and this is 25, right? And now you check once again that the law of continuity is maintained, and I'll stop over here that the law of continuity is maintained, and I'll share some notes with you in the class materials section from the SK Garg book if you guys are not having, and you just go through that particular that particular portion. There are 15 or 16 pages which are taken from this particular book, you go through the Hardy-Cross method, you get to know how the calculations are performed, and we will do that numerical, this particular numerical in the next section. And this numerical has been taken from the book itself. So if you have any doubts, just write them in the Teams. Okay, and I'll just check whether the recording is on or not. Yeah, I think recording is on. And just in case if the recording has missed some part, that's okay. You have any doubt with this thing, you can text. Only with this particular topic which I have taught. Regarding all the topics, you may have to talk to other TAs.
Sir, can you share the whiteboard pics?
Yeah, that I will share. I'll share the image of the whiteboard. And don't leave the meeting. I'm stopping